Alrighty, hi everyone. We'll get started. How are we doing today? Good, great. Okay, we're almost out of the semester, which is kind of crazy. Thank God. So just briefly before we get started, I know that your final is coming up, right? You still have a couple weeks, but that is coming up. So in terms of review sessions, like what would you like to see from me? I will be having one next week, and then the week after that, I think, is technically a reading day on that Wednesday. So I won't be having this usual session. So I think next week's our last one together. So what would you like to see instead? I can either do, I guess I could still hold it in here if you would like that on that Wednesday. Or I can do a Zoom review session, or I can do something earlier in the week. What are we feeling?
Earlier that week, because I know I have it like that Tuesday or Thursday.
right?
Thursday.
Yours is Thursday, Altman's is Thursday. So I wasn't sure if Wednesday was like a good day or a bad day. So I can do something earlier in the week, like a Monday?
Yeah.
Monday, okay. So we'll plan on a Monday and then maybe also a Wednesday. And that'll probably be the two things that I do for that. Do you want that in person or on Zoom? No preference?
I feel like in person it's a little bit more interactive. Yeah.
Yeah. Okay, so we can do it in person. We'll do it maybe in person on Monday, or maybe in person Wednesday, and then maybe Zoom Monday or something. Either way. Okay, but I'll plan on Monday and Wednesday for those. Cool. I just need to make sure I have a room booked. Okay. But enough about scary finals. What about today? What are we feeling? What do we have questions on?
Stops fun, like whether penultimate is spontaneous based on delta G. Well, like not whether it's other negative, I guess like waiting.
Like in using delta H and delta S at the same time? Yeah, absolutely. Okay. So what is that equation that we're talking about for delta G when it uses delta H and delta S?
Delta G equals delta H minus S.
Beautiful, right? So delta G not is equal to delta H minus T delta S. So, right, just like with every equation, these are all important components. So what is delta G? What do we call that?
Gibbs.
Yep, perfect, right? This is Gibbs free energy. Everyone can see that. What is delta H? Close. Enthalpy is this one. Yep. Delta H is enthalpy. So delta S is entropy. And T is what? This is in temperature. And what unit is temperature in? It has to be in Kelvin. Perfect. Right. So the important note with temperature being Kelvin is that it's always positive, right? Kelvin cannot be negative in this case. So temperature is always going to be positive. It's always greater than 0. And therefore that negative sign is either going to be determined by that delta S, because T will always have a plus sign in front of it. I don't know. Anyways, alrighty. So when we talk about enthalpy and delta H, what does the world prefer for delta H? Right, the heat of the reaction. What sign do we want the world, or what sign would we prefer all of our reactions to be? It's actually negative. So we want delta H to be negative. Right, we want delta H to be giving off heat. What do we call a reaction that gives off heat? Exothermic, good, right? Okay, so the world prefers reactions to be exothermic. What about delta S? What does the world prefer the sign of delta S to be? Do we want a lot of disorder or a little disorder? A lot, right? So that's going to be that positive S. Why it prefers to be exothermic? That just means the heat is being released. So that means that that heat is now available for other stuff to use. I don't necessarily know exactly why it prefers it, but I do know that if you had to pick between an endo and exothermic reaction, we want the exothermic reactions. Probably because of this whole equation here. but you prefer your heat to be given off. I think that's just so it has, the universe now has more heat to use. Alrighty, so the world prefers an exothermic reaction and it prefers a disordered reaction. So that means we have a negative delta H and a positive delta S. So if we look at delta G is equal to delta H minus T delta S. If we plug in a negative sign for delta F, for delta H, right, that makes that first term in our equation negative. We then have minus, what is the sign of temperature? Positive, times what's the sign of S if it's our preferred reaction? Also positive, right? So now we have negative minus a positive, which if we think of keep, change, right? We have negative plus a negative. So does our delta G get more negative in this case or more positive in this case? It becomes more negative. In this case, delta G will have to be negative because we're taking a minus plus another minus. We're just getting more negative in all of our situations. All right, this turns into be the same as saying that. All right, so delta G becomes negative. So if delta G is negative, is this a spontaneous or a non-spontaneous reaction? This is a spontaneous reaction. Right. So when delta G naught is negative, then we have a spontaneous reaction. But sometimes we don't have a negative delta H or is there questions on how we got to that conclusion? Does that make sense? Okay. Like why did those signs end up negative or?
Yeah, like why is it
so that's just saying that, right, the world prefers the exothermic reaction and the disorderly reaction. So if we have a case where the reaction is going to increase our disorder, right? So maybe we're going from liquid to gas, and we're also releasing heat, then that's going to happen spontaneously. You don't need to put in any work to it. It's actually going to give off work for it. So that's why we say it's spontaneous. You don't need to add anything else to it. It will just happen. I don't know of an example off the top of my head of something that's exothermic and increasing disorder, but I have a couple other examples that we'll see later on too. But right, so if both of those world preferring reactions happen, then your overall reaction is going to be spontaneous. Always spontaneous, doesn't matter what temperature you're at. But we could have different combinations. So one that I always like to look at is ice melting. So if we're going from solid to liquid, what's our delta S on that equation? It's increasing disorder, right? We're getting from something that's less rigid to, or something that's very rigid to something that's less rigid. So delta S, it's going to be positive. But what has to happen in order to go from solid to liquid? What's our delta H here? It has to be positive, right? We have to put heat into our system in order for it to melt, right? So our delta H here is going to be positive. So in our, say it again. Yep, so it's endothermic. This is an endothermic reaction that's increasing an disorder or increasing entropy. So in terms of our delta G, we now have a situation where we have a positive minus a positive. Right, T is always going to be what sign? Positive. So now if we bring that all together, right, we have T minus a positive minus a positive. So at what temperature does this, so is this reaction spontaneous? Yes, no, or we don't know enough.
It's certain temperatures.
It's going to be at certain temperatures because at low temperatures, right, maybe we have a delta H of 1,000. At low temperatures, let's say 1, right, maybe our entropy is only 100. So in this case, our 1,000 is beating out our 100. And so we still end up with a positive delta G. And so that's going to be a non-spontaneous reaction. But let's say we have our reaction happening at 100 degrees Kelvin. Our enthalpy and our entropy still stay the same at our different temperature, but now we end up with 1,000 minus 10,000. So what does our delta G become? Negative. So as we increase the temperature, our reaction becomes more spontaneous. We can think about that a little bit too. If you put an ice cube in your freezer, is it going to melt or is it going to stay an ice cube? It's going to stay an ice cube because it's cold. If you put it at room temperature, what happens to your ice cube? It's going to melt, right? So you've now increased your temperature. You've now taken a non-spontaneous reaction and made it spontaneous, right? You don't need to put in any effort. You just need to take your ice cube out. It's going to melt. Does that make sense of how that's happening and the difference between that? So when it's positive and positive, this is going to be spontaneous. Wow. At high temps. What about if it's negative and negative? When do you think that's going to be spontaneous? Beautiful. So we said if it's negative and positive, it'll be spontaneous always. If it's positive and positive, it's spontaneous at high temperatures. If it's negative and negative, it's spontaneous at low temperatures, which is easy to remember, right? Because you think plus, that means you're adding, so that's high. And if it's negative, that means you have to minus, which is low, right? So then if it's positive, endothermic H, and then negative, you're decreasing disorder, when do you think that's going to be spontaneous? Yep. Right, delta H is positive and delta S is negative. So we're requiring heat and we're also decreasing disorder. And it's never going to be spontaneous, right? Yep, right, because your positive will always be in front. Your negative times your negative will make it a positive. So your delta G, no matter what temperature you're at, will always be positive. And in this case, that means that the reaction is not going to be spontaneous. That doesn't mean that your reaction doesn't happen. It just means that if you set it up and let it go, it wouldn't be fast. It wouldn't happen. You have to do something else. You have to put work into it in order for it to go.
And those are conditions opposite of the ideal.
Right? Those are going to be opposite of what the world prefers. Or that ideal case. Any questions on determining the sign of what that is? Alrighty, and then just to tie it back into this last bit of our chapter, when we looked at our phase diagrams, right, whenever you're going up this graph, these are always going to be endothermic reactions. And as we're going down, these will be exothermic. Okay, so if you're thinking about what's happening to my or like you're given an equation, you have to predict like what delta H is gonna be, right? If you're starting from an ice cube and going to gas, or you're increasing, you need to put heat into the system in order to make that happen. So it's gonna be an endothermic reaction, but you're also increasing entropy at the same time. And then the reverse happens, equal and opposite on the way back down. So just in case that pops up. Alrighty, what other questions do we have? Yeah.
I think like the bomb calorimeter stuff,
Mhm.
and then just like how to go about like solving the practice problems and the like equation
Mhm.
of it.
Just like recognizing
Yeah.
something like that? Yeah, absolutely. So. So when we talk about calorimetry, what is an equation you usually use for it?
See.
Mhm. Yep. Beautiful, right? So Q is equal to MC delta T. This is our big equation when it comes to heat transfer and everything, right? Just like that. So this comes into play for calorimetry. This comes into play for phase diagrams. Any sort of chance that way. When we're looking at, right, delta C, or when we're looking at C, this is going to be your specific heat capacity. Your specific heat capacity is usually given to you in joules over grams times degrees Celsius. And that's important to remember because if you're just given a regular like system and surroundings equation, right, where maybe a piece of metal is dropped into water, that's going to be specific heat capacity, and you're given both of those in that kind of unit. When you're talking about a bomb calorimeter, usually it's just going to be in joules per degree Celsius. So it takes rid of that gram component, but it already takes into account the grams for that bomb calorimeter. So that's a way to recognize between the two of them because you don't have those units that are the same between the two, right? So just visually looking at your questions, that's really a good thing to pay attention to. And right, then you don't need to worry about a mass, right? Like I don't have a mass because it's already taken into account. Okay. Let's see, what else? We can talk about right, they call it constant pressure. Calorimetry. And this is when you're going to use water mostly. Right, so you're going to use Q is equal to MC delta T, but it's going to be the Q of water, which is equal to the mass of the water, C of water, and then the change in temperature of water. Right, you use that, and then you'll compare that to Q calorimeter, which is where it's now just C delta T, right? In this case, the C doesn't have that gram component. That's already taken into account. Okay. And then you can say that your Q system is equal to the negative Q water plus Q chem. So you have two different Qs that you're solving for that you can add up, which will be your surroundings, right? Your water and your calorimeter. And then your system is that positive Q. It doesn't really matter really which one gets the negative in these situations. But you just know that your water and your calorimeter are gonna go together, and then everything else is gonna be your system. That's just a quick breakdown of that. Does that help a little bit just with recognizing? Okay. And then sorry, this one's a little long, but I'll write it down. I'll minimize the words as much as possible. Alrighty, right, so for this question, we have a 1 gram sample of octane is what this is burned in a bomb calorimeter containing 1,200 grams of water and an initial temp of 25 degrees Celsius, and your final temp is gonna be 33.2. And you're given the specific heat of the calorimeter and then the specific heat of water. And we wanna know to calculate the heat combustion of octane. Okay. How would we start this equation? What do we need to do first?
That whole thing of like water.
Yeah, perfect, right? So we want Q is equal to MC delta T, and we're first gonna solve this for our water. So what's the mass of our water? We have 1,200 grams of water. Beautiful, right? We have our specific heat, which is 4.184.
33.2 minus.
Beautiful. Perfect, right? So we have our grams or we have our mass in grams, we have our specific heat, and then we have our temperature. Temperature is going to be T final minus T initial, so that's why 35 or 33.2 is minus 25. So our Q water is equal to 4117056 joules. And now our combustion of octane is asked for it in kilojoules per mole. So what should we do to our joules here? Divide it by 1,000 and get it to kilojoules. So this will be about 41.2 kilojoules. Okay, does that end our equation or end our question? No. What do we need to do next? Very close. We're gonna add it to this number. But yep. Right, so we're gonna do the same thing, but this time for the bomb calorimeter. So this time Q of the calorimeter is just gonna be C cal times delta T. So this is 837 joules per Celsius. The same change in temperature. So your system here is your reaction burning. That is a combustion reaction, a endo or exothermic reaction? It's exothermic. So everything else around it will absorb that heat. So that's going to be the water and the calorimeter are all around your reaction. Those are the things that increase. Okay.
Diameter never have mass.
So the specific heat, the 837, that's taking into account it's a mass already. So it shouldn't give you a mass in your equation because it's already taken it into account.
On the quiz, there was like a word described specific heat of it wasn't, it didn't say specific heat, it said something else. Not the same meanings.
Would it be the heat capacity?
No, it said something else, but
Okay, I don't remember. Or I don't know what word it would have been, but usually it doesn't have mass associated with it. Yep. If it's in joules per degree Celsius, then it's your specific heat capacity. Alrighty, so then your Q cal is equal to 6863.4 joules. And what should we do to this one? Also divide by 1,000. So we get 6.86 kilojoules. Ready? And now what do we need to do to our two Qs that we just found? We need to add them, right? So we know that Q of our system is going to be equal to negative Q water plus Q cal. So Q system is equal to negative 41.2 kilojoules plus 6.86 kilojoules. So our Q system is negative 48.1 kilojoules. Q system being negative, does that make sense? Good. Perfect, right? So we know that a combustion reaction is exothermic, it has to be releasing heat. And we know that our water and our calorimeter are getting hotter, which means it has to be absorbing heat. So in order for our system, or order for our surroundings to be absorbing heat, our system has to be releasing heat. So that predicted negative sign is we observe within our final answer as well. So that's always a good check for these as well.
A bomb calorimeter is usually combustion reaction, so those usually be.
I don't know. I think other things other than combustion can happen in bomb calorimeters, but I feel like for the most part, they usually ask about combustion. But I think other things can happen.
It was like challenge for the field system was certain number of grams of a substance, and then but it had to be converted into moles for some reason because they don't want to do molar combustion, heat of combustion. Like, how would we do that in the service?
Yeah. So
What is this one? Cause didn't you? These are just per month.
yep. So, right, this is just for our, right, combustion reaction in kilojoules. But we were given that we have 1 gram of the C8H18. How can we get from grams to moles? We can divide by the molar mass. So we can get 1.000 grams of C8H18. And then this is 1 mole equal to 14 grams. We end up with this many moles of C8H18. So how do we get kilojoules per mole? Take the kilojoules we just found and then divide it by the mole. So we'll take 48.1 kilojoules divided by 0.00877, should be negative. And we end up with 5483 kilojoules per mole. So in this case, if it asks for a gram or mass of something and it asks for it in kilojoules per mole, you really just need to use your molar mass and then divide by your final answer. Yep. It's nothing too crazy. It's just a little tricky to like remember to do that. Yep. Yeah. If they give you the grams of your starting material, then you can usually just use molar mass to find that one. Yeah. Great question. What's that? Do you have another question? Okay.
Or is that
So it's like the bomb or like the styrofoam cup is like the two that you usually use. Same thing happens for both of them. Yep. And then a normal calorimeter is when it's right, you have Q system is equal to negative Q surroundings. So then you have MC delta T is equal to MC delta T. So like maybe just your water and your piece of metal that you're dropping, those two things. Right, one of them's hotter than the other, so then they reach the same final temperature, and then that's the other kind of version. Yep, yep. It would be like a piece of copper metal at this weight, at this temperature, is dropped into water, and they reach this final temperature. How much water did you have?
so when they question fails? Any like specific feature for that's usually
Yep. Because they would give you the specific heat of the metal and the specific heat for water. So if you have the metal and water, then that's what's going to be like, okay, this is the equation I use here.
Can you do one where it changes between the different phases from like let's say solid all the way up to like
Yeah, absolutely. think that should be everything. we need. Okay, so you have a 1 gram sample of ice at -20 degrees Celsius is heated to 75 degrees Celsius. And what heat is required to do this is the question. Anyone have an idea of how we're gonna solve this one?
Probably start off with that, C and then like delta T, right?
Mhm,
T.
yep. So does anyone know how many total Qs we're gonna need to solve for?
Three.
Should be 3, right? So we need to have our -20 all the way up to 0, our phase change of solid to liquid, and then our 0 to 75.
Draw a picture.
Yep. So we are starting here. We need to do this portion, and this portion. So we'll have 2 QMC delta T's, and we'll have 1 of our heats of fusion. Do y'all want to try this one or walk through it? We try it? Yeah, we can try it. I'll give you like a couple minutes and then I'll start going over it. Yeah, you can assume normal for water. Okay, so how you're gonna start this is just by doing MC delta T plus N times the delta H of fusion, and then your second MC delta T. So your first MC delta T is gonna be which one, the 4 or the 2? The 2, right? Because you're starting off with ice. So your specific heat for ice is different than your specific heat for water. So what's your mass? 1 gram. We said our specific heat was 2. And what's our delta T here? Just 20, because we're doing 0 minus -20. So this is going to be 20 degrees Celsius. What is up with that delta H of fusion?
Phase change. So it's just delta fusion times the mass. But the unit is different.
So the unit's different, but what do we need to do to those units? Good, right? So our heat of fusions is in kilojoules per mole. So we're given grams, so kind of similar to what we just did where we needed to use that molar mass. we have to find the molar mass of water and convert our grams to moles and multiply it that way. So this case, 1 gram is 1 mole over 18.02 grams. So that's 0.0555 moles. So now we can convert that or plug that in. And we end up times 6 kilojoules per mole. And then what's the last MC delta T? What are we plugging in there? And this time we're doing 75 minus 0, so that's just 75. Okay, so we have 41.334 kilojoules and 313.8 joules. Can we just add all those up? What do we need to do? Convert them all to the same one. I'm going to convert the kilojoules to joules. And so now we can add all of those up. And we end up with 689.6 joules. So what was that round to? I mean to say like. Oh. And our Q is positive. Should our Q be positive here? Yeah, it should be, right? We're heating it up. We're doing a phase change. We're increasing. We have to add heat into our system in order for our ice cube to melt. So a positive Q is expected.
Why is your formula for the second Q there?
Yep, so in our second Q, right, we're at this phase change here. And when we're at the phase change, there's no change in temperature. So if you use the MC delta T, then you would end up with a Q of 0, but we know that we need to put Q in. So the way you change that is multiplying the mass times the heat of fusion. Yep, and the same thing happens for your boiling point as well. So you would just have the delta H of vaporization for the boiling point. Yeah, it'll be times mass or times moles in this case. We did, you just pay attention to the units that they give you in the equation. Does that help your question? Awesome. What other questions do we have? Calorimetry make a little bit more sense? Yeah. Anything else at all? All experts? What's up? Yeah, absolutely. Let's do. All right, so for this one, we have a 3.52 gram piece of copper metal at 95.3 degrees Celsius is dropped into water at 25 degrees Celsius. And if 10 grams of water is present, what is the final temperature? How do we set this one up? Right, so we can say that negative Q water is equal to Q copper. In this case, right, if our copper is at 95 and our water is at 25, which one's going to be absorbing heat? The water is going to be absorbing heat, and then your copper would be releasing heat. So you could switch your negatives if you wanted to, and then your negative copper would be a negative times a negative. Or in this case, the negatives are going to cancel it anyway, so it's not too bad. Okay, how do we set up our Q of water? Perfect. All right, so we'll have 10 grams, 4.184. We don't know T final, and we know that we're at 25 degrees Celsius. That's going to be equal to the same thing, but for our copper. We have 3.52 grams, 0.445, and then T final minus 25 degrees Celsius. And then it just becomes an algebra problem from here. Oh, yes, it is. Thank you. Yep, 95.3. So now what I would do is I would combine your 10 and 4.18 and your 3.52 and your 0.445. Make those two numbers and then distribute them so that you can combine T final onto one side. So math is a little wonky because I made up these numbers myself. So your T final is 22.28, I think, if I did that correctly. Can someone tell me why this doesn't make sense as a final temperature, but is technically correct? What'd you get? Oh, that would probably be good. 27? Okay.
And that's, I think it's in the 148.
The 1 point,
The one.
what am I doing?
I got 43.2. Or like 43.406402.
Did you get 148.32?
No, I got 149.26.
Oh, there it is. Okay. Okay. Perfect. So then this. Then you got 896.72. Okay. And then. Did you have 40.283?
I didn't know, I had the thing this way. Oh,
Okay.
it's because of the negative is missing on the right side. It should be plus 149.28 minus 1.566. Or like one of the left or the right needs to have the overall negative.
Oh, yeah, I dropped it. I dropped it from the very beginning. There it is. There it is. Right, all of this has a negative. Perfect. Okay, yeah, there we go. So then. Okay, this is still 89. Let me just write this again. Okay, so then this should be 1046 plus. Okay, great. I knew something was wrong. Okay, perfect. So our T final should be 27.54, which makes more sense because that's between 25 and 95. Great. Thanks for the help, y'all. See, and this is why you check your answer and you ask, does this make sense? I said no, but I rolled with it. Right, so the important thing here is that I dropped my negative when we first plugged everything in. Right, so one side needs to make sure that you have your negative for the exo or endothermic. And that will play a key role later on when you have to distribute that into everything as well. Okay, so your final answer should be about 27 degrees Celsius. Does that help with the T final? It's definitely like the hardest that you can ask for these types of questions. Lots of room for error, so. Alrighty, any other questions this evening? Okay, well, it is 6:30, so I can wrap it up for today. Thanks for coming. I hope that was helpful. And then just keep out on the lookout for an announcement from me and I'll kind of make sure I have everything ready to go for final stuff. And yeah, if you have any questions in the meantime, just feel free to ask, send me an email and I'll be happy to help. Thank you.